Yeah, not yet.
No worries.
Hey, Mary, I have uploaded the YouTube link, so you should have it.
Okay. Yeah, I won't be able to watch it before this meeting.
Yeah, that's
No worries. I'll watch it later.
yes.
I usually use my laptop, or like for like, yeah, like I don't have a webcam for my desktop right now. So when but it can be a confusing. So like my habits can get in the way then when I put my laptop in front of me, but I also have my desktop keyboard in front of me.
Okay.
And I use like key bindings, so like closing windows. I close a window and I see that I accidentally did it on my laptop when I meant to do desktop or vice versa. Crazy. Anyway. So I'm happy to wait as long as you guys want. If you want me to start at any point, just let me know. What are you thinking, Yogesh?
Last 1 minute and we can start it.
Sounds good. Oh, I see. I'm in one meeting on my desktop. Oh, well, I'll just do it on my laptop. It's fine. Okay.
I think we can start.
Sounds good. Just share my screen here. All right. Just ignore all this stuff right now. I'm just pulling up slides in a semi-awkward way, but all right. Here we go. All right. So I'm going to be talking and I'm going to be presenting on convolutional and recurrent neural networks. This is an extension of the stuff that we did last week, where we were just trying to do an introduction to neural networks in general. Now, I don't know, so I guess if there are any questions, please feel free to jump in. I try to, like last week, my goal is to try to start a little bit higher level, make sure we talk a little bit about the conceptual landscape and stuff, and then of course jump into an actual concrete example or two. The challenging part is that neural networks and deep learning in general is a very broad space. So so I don't want to spend a huge amount of time diving into all of the little details just because we don't have time for it. That said, if there are any details people are interested in, I'm happy to discuss to the best of my knowledge. All right, so basically this is a brief overview of what I'm planning on covering for the day. First, convolutional neural networks. I was hoping, I'm trying to look at the participants again. Okay, good. Himanshu's here because he was here last time and had questions or had questions about one of the examples. And anyway, first talking about convolutional neural networks, some of the basics, and then a little bit more of the details about convolution and pooling layers, and then getting into some recurrent neural networks. Again, more like basics, a little bit of recurrent or examples of the recurrent layers, and then getting into a few examples, some related demos, a hands-on example, of course, you know, all that kind of stuff. So, and a lot of, and I do borrow some slides this week from Stanford, just because they have some nice examples, I think, where they dig into convolutional neural network or convolutional layers themselves. So, so some of the basics. Last week, you know, we mentioned that a neural network is simply a sequence of differentiable functions, where each of these differentiable functions is represented as a layer, with most sort of, I guess, abstractions or representations. Now, I mean, it's the only little asterisk I would put by this definition is that they can have like branching and merging in these functions. So in other words, it's not necessarily a sequence of functions. It can be a graph of functions. This is related to topics about computation graphs and implementation details, kind of like that, which we might have time for at the end, and I'm happy to jump in there to expand on that. But basically just saying it doesn't have to be solely sequential. There can be branching and merging in these architectures, but that's the only little like caveat I'd put there. Now, a convolutional neural network is simply a neural network that contains convolution layers. At a high level, the big important takeaway is that these convolutional layers or convolutional neural networks are really useful when data is 2 or 3 dimensional, or when the input itself is, such as like images. It's also worth noting that this the higher dimensions should provide some meaningful information for the given task. In other words, you could certainly make arbitrary data 2-dimensional, but that doesn't necessarily mean that a convolutional network is going to do anything useful. But if we compare this to like an image, where individual pixel values may not be useful, but how they are positioned with respect to others is really useful. So their spatial information, I guess, or their neighborhood information, because then they can start to form edges, and edges can start to form shapes, and you have these kind of layers of abstraction on top. All right, does that make sense so far? Again, we haven't gotten into the weeds yet, but just trying to lay a little bit of the foundation.
Sounds good.
Cool. All right, so I was, I guess, I don't know, lazy maybe? Didn't even try to paste them in. but anyway, so we're gonna jump to slides 2 through 20. This should be slide 2. All right, so the formal, like, I guess, mathematical specification of a convolution isn't terribly like essential to understand here, but basically, because we'll see a concrete example of what this means in the context of neural networks in a moment. So I'm just going to kind of gloss over that part. I wanted to include this just as a little bit of a refresher, I guess, or a little bit of review for some of the representations that we talked about last week. So this is a neural network with an input layer on the top here. So the data is all of these neurons in this first column on the far left. And then they have some sort of intermediate representation, which is captured by this hidden layer. Now these lines, of course, to each one represent a weight. So for each hidden layer, each neuron in the hidden layer, its value is determined by the weight times the input neuron for each incoming edge. And then, so in other words, it's just a linear combination of the inputs. And then of course you generally have some nonlinearity placed on top of that, you know, because if you don't have a nonlinearity, adding a bunch of these linear operations can all be reduced to a single linear operation. So so adding layers doesn't really help. But these nonlinearities may be things like just the max between 0 and the number. It might be things like hyperbolic tangent. It could be things like sigmoid, things like that, softmax. Now, I'm not going to spend a lot of time on this part. Here we go. All right, so this is basically just saying what I just said in the previous figure. So, so basically the value of A1 here, which is, so X is your input nodes. Oftentimes they include an additional node or add basically, or sorry, an additional neuron here that just has a value of 1 just to like account for any bias that might need to be captured by the network. So, so as you can see in the first function here on in the top, that the value for a single neuron, in this case A1, is simply the weight times the input for every incoming connection. Again, in this case, they're including the bias as well. Now this F is the nonlinearity. So this could be like, sorry, nonlinearity, also known as like an activation function. So basically this, again, could be sigmoid, softmax, hyperbolic tangent, ReLU, or ReLU is the max between 0 and the number. And sometimes you'll see the similar notation here, and this is computed, of course, for every neuron in the next layer. As you can see here, they have A2 and so forth. Now at the bottom, they have a matrix representation here where they have the weight vector represented by capital W multiplied by X, which is all your input, or the inputs to the layer. And then they're adding some B vector, which is just a bunch of biases to account for any like basically initial like offset. Now Z here, Z in machine learning is often representing like latent variables or latent representations. So in other words, some sort of intermediate, representation or value. And then they, and in this case, you can see that Z is simply this linear operation, which they're using to compute this A vector by, again, applying the activation function. All right, I hope people don't mind this little bit of review. Oh, is there a question?
I appreciate it.
So the activation function,
Mm-hmm.
usually people don't talk about what activation functions to use because I see that there may be a dramatic impact of which one do you use in which particular problem. So how do you go about choosing? You can always do a hit and trial, and with experiments you can figure out which one works better. But is there like a general guidance or insight?
So there are some like shortcomings known known about certain ones or about some of them. Generally, I start with just starting simple and then adding complexity as you go. ReLU, for example, in other words, the max between 0 and 1, is known for, or at least one of the risks with it, is that you can have neurons that that they say like die. Basically, what this means is if you think about the derivative of the max of this function, which is max between 0 and 1, it's going to look kind of like I think they sometimes call this the hinge function as well. But anyway, so so the problem with this function is that once a neuron's value is below 0, then this max operator will always return 0. So in other words, the slope for those values is nothing. So then these neurons can kind of die, because when you're computing the gradient can often be 0 and they just kind of stop. Does that make sense? Okay, that's a bad example. Okay.
Yes.
Wait, it made sense, or it's a bad example?
It made sense.
Okay. I mean, it sounded like you were agreeing to one of those and I wasn't sure which. So I'm going to pull up some of the documentation for a list of, let's see. I mean, a lot of times we look at loss functions here, but let's see. Do they have a list of activations here? So a lot of times you can find some information about these. I mean, some of them are fit for suited specific tasks, like softmax, for example, will push things into a probability distribution. So that one is usually used at the end of the network. That's used for classification. Let's see, like hyperbolic tangent's not a bad option. Okay, Yeah, and so I usually start with simple like ReLU, and then as needed, I might move to like hyperbolic tangent, things like that. The challenging part is that some of these can also be, some of these things can also be related to the network that you're using and things like that. You know, like we'll see a little bit with the recurrent examples that that some of these networks can have problems like the vanishing gradient or exploding gradient things or problems. So like the activation function you can use, I think, can also contribute to this. As the short answer is, I would recommend starting simple, and then adding complexity as you go. ReLU is pretty commonly used, or at least that was one of the first one that was commonly used, and so I think it's a decent starting point, or like starting point. Let's see. I mean, yeah, I mean, that's generally what I'd recommend. If you like, there are others to explore and to try out as well. And if other papers in a similar domain have been using a different one, sometimes they'll have justification for why.
Okay, thank you.
Yeah, yeah. Hopefully that answered it semi well. All right, so so moving forward here. All right, so so as I mentioned before, convolutional neural networks are useful whenever you have like 2 or 3 dimensional data. You know, most commonly they're used for images. And in this slide, you know, they talk about like, why can't we just flatten the image and feed it through the neural network? And the short answer is that you can. It's just a lot harder to learn now because you lose a lot of that spatial information. Like, you still have this information, but the information would mean, like, if you want to detect a vertical line, you have to detect you have to have a network that learns that there's a pattern like okay, so suppose you want to detect a vertical line on 32 by 32 pixel images. You would need a network that detects that every 32 pixels it has to be a certain color. Does that make sense?
Yeah.
All right. So you can do it, but it's a lot harder. Convolutional neural networks have been like really effective in this area. Now, at a high level, this is essentially what they're doing. This is a volumetric representation of a neural network. So you can see that the input here is like a car, but they have 3 little layers there on the left, representing like your 3 like red, green, and blue channels. And then they have a convolutional layer here, which as they try to imply kind of that by the sizes of these volumes, you know, that you're doing some sort of downsampling where you're trying to detect things like features or edges, or like features like edges or things like that. Basically, you're learning filters to apply over the image to try to detect something that's meaningful to the end. It's always funny mentioning things that I guess hand wavy, saying something meaningful. When I say something meaningful, I mean something that decreases your loss during training time. And then of course we have these pooling operations, and pooling operations will take like the maximum or minimum of a region, whereas again, convolutions are learning meaningful filters. The max, min, and average pooling and such are just you know, selecting the max, min, or average of the region, giving you a little bit of like, I guess, invariance to some of these like wiggles and where in the location of where something is. All right. Oh, and convolutional networks generally follow this structure. You take some sort of 2 or 3 dimensional input. You have a bunch of convolution and pooling layers, and then at the end you flatten, like you see on the right here, and then you'll pass it through a few, like just basically a regular neural network as the sort of tail or end of it. You generally don't. I don't think I've ever seen convolutional layers. I mean, like okay, it's very unlikely, especially for like classification or regression or things like that, that you would ever want convolutional layers after like fully connected layers. I say it that way and I say very unlikely because there are some very clever and goofy downsampling and upsampling networks, but for most intents and purposes, you'll see a bunch of convolutional layers at the beginning in which they flatten it into what is hopefully a meaningful representation of the image, and then they'll pass it through a few fully connected layers. And in this case, you can see on the far right, it says softmax under the last layer. and they have little labels by each neuron. So you can see that they're trying to do they're assuming that this is a classification problem, and they would, for that purpose, use softmax to make sure that the output is a probability distribution, and then of course assign each element of the output vector one of the classes. Yeah. All right. Now the details of a convolutional layer is kind of visualized here. So in the middle column here, we have the input. So suppose this is some image or at least some input data. Actually, well, suppose this is, let's just suppose it's an image. The top one is one channel. The middle one is another channel. So these could be red, green, and blue from the top down. They tried to show that here with this, MATLAB or Python-esque notation, where it's X, all rows, all columns, the first channel, X, all rows, all columns, middle channel, and X, all rows, all columns, last channel. Does everyone see what some of these things are easier to do when you're in person and able to point to parts of the slides better. But basically I'm referring to this the notation right above each matrix. All right, so we have these grayed boxes around the edges. These are zeros. Now one value that you'll often hear, or one, I guess, parameter of a convolutional layer is usually how much padding you want to add to the image. So basically that's how much, like this would have this example has, 1 unit of padding added to the top and to the sides. Now, here I wanted to hide this. Oh well, I'll just scroll up a little. All right, yeah, so you can see it has the plus pad 1. Assuming that it's a 7 by 7 by 3, so 3 channels. We could imagine this is an image with 7 by 7 image with red, green, and blue values, normalized, or well, not quite normalized. I would expect them to be between 0 and 1 if they're really normalized, but, but anyway. All right, now, so when you're feeding this input into a convolutional layer, essentially you have some number of filters that you're applying. Now each filter, so we have, all right, so we have 2 different filters where it's running a separate, or 2 different, I guess. Yeah, so we have 2 different filters, but each of these filters has a different pattern that it's looking for in each channel. Now the first filter, this W0 in the top here, so is applied to the first input channel. So I feel like I stumbled over my words a little bit with some of that. Do people understand what I'm saying, or should I clarify this a little more?
I think you should clarify.
Sounds good. Okay, so so this convolutional neural network has filters. The filters determine the output of the network, how many basically channels or the equivalent of channels you're going to have. Now, each individual filter has channels, or shown here as these 3 rows in red. Each channel, or you could imagine it as like it's the individual values applied to that filter. So this would be like, this top one, this W0, is going to be computing the basically edge detection, or it's going to be convolved over the red channel. The second one is going to be convolved over the green channel, and then the third one over the blue channel. You could imagine that this is looking for like certain types of edges or patterns across the red channel, the green and the blue, which of course, when it's all combined, hopefully is similar to us detecting edges visually. Hopefully it helps to like walk through exactly how they compute all these values. So basically this, in this first one, we have W0 being applied to this bluish region in the top left. So essentially what it's doing is it's going to do a scalar product here. So we're going to take this, we're going to multiply, do a pointwise multiplication. So this is going to be 1 times 0 plus -1 times 0 plus -1 times 0. Then that's the first, for the first row. Then this is going to be added to -1 times 0, 0 times 1, and 0 times 2. And then across the bottom row, we'll have 0 times -1, -1 times 2, and 0 times 2. So the overall value computed for this across the red channel for filter 0 is going to be -2. Does that make sense?
Yes.
Cool. All right. So we're going to do the same things for the next one. We can see that the first row and first column for all of these are actually landing on the padding, so they'll all be zeroed out. So so the only thing we really care about is the bottom right, like for values. We can see the top two are 0 for, if we're looking at the green channel, we can see that we're going to get another -2 because the first row is all zeros, second row, or the first column's all zeros. So then the second row has only zeros in the filter. So then the only thing we care about is really the second and third columns of the third row, which are -1s, which are multiplied by 1. And so resulting in a value of -2. So we have -2 as the output for the first channel, the first channel of the first filter, and the same with the second channel, the second filter, first filter. And then we end up getting -3 for the third one, but they also have a bias value of 1. So you can see that all these values together end up getting us -2 plus -3, or -2 plus -2 plus -3 plus +1, which is -6. And we can see that in the output volume in the top left quadrant for the first channel, or for the first filter, sorry.
Oh.
Okay, so does everyone understand how that -6 was computed?
Yep.
All right, so okay, so after you compute the first one like that, basically these also have convolutional layers, also have a value of strides. So in other words, how much do you move over as you keep computing this? So like I'm assuming, or I think since they didn't specify it here, I'm assuming the stride is 1. So so that means that after they apply this first filter, or W0 to the currently highlighted region, it just shifts over by 1 on the input volume. And then we recompute the whole thing, and that should give us -7. And then we scoot over one more time, get to -5, and so on and so forth. Actually, it looks like their stride is 2. But anyway, so basically we just have this sliding window, as you can see, that moves across the image, doing this scalar product, or computing this scalar product, and the output is, and then returning that, or producing this as an output. Now the values in red, in the dark red, or any of these red filters, are the weights or the parameters for that layer. In other words, when we do back propagation, these are the values that we're optimizing to try to minimize our error or our loss at the end. So that's how these are, these individual values are like trained. That's where these filter values come from during the training process.
This 3x3 is called the kernel.
Yeah, so this would be like the kernel size. When some neural networks or some libraries will call it like a kernel size. So if you said like I think in Keras it's kernel size, and you pass a tuple like 3x3, or 3,3, and then that would be what this is. And then some of them will also say number of filters. Number of filters corresponds to like of course each of these columns. So this has 2 filters, and of course each filter has 3 channels, where each channel is applied to the corresponding incoming channel, or the corresponding channel of the incoming input. Oh, here, I guess I could have just scrolled down to show the next step. So we see that it moves over, and it is a stride of 2, so that is confirming that part. So I'm surprised I didn't mention that, but anyway. So we slide over, we compute the next value that way, and then we continue. Now the second row of the output volume in green here, of course, it corresponds to the outputs produced by the second Wern filters, so filter W1. All right, let me just continue on. So this is also why I didn't really want to get in, or although I used an image classification problem last week, I didn't really want to get into the details of the convolutions because I just wanted to mention that they're just another differentiable operation. And this is really what they are, and this is why they're well suited for images, because because you can see that these are specialized to look at specific regions and try to detect patterns there. you can imagine that if this is a fully connected layer, any of these could affect any other. So trying to bias the layer to really learning these local patterns would be a lot harder. Hopefully that makes sense.
So this makes sense. With the convolution steps, like convolution layers, one after the other, you are focusing more on the aspects that really matter, and trying to forget or at least remember less the other aspects that don't matter that much.
Yeah. So you're trying to learn these like a more important representation or an abstraction on top of it.
Yeah.
An easy way to think of it intuitively or conceptually is like if you have multiple layers, the first layer might be learning like little edges, like little lines.
Yeah.
And then that means, and then when when it produces an output that's like a 1 for a line or some value for some numerical representation for like vertical or other types of lines, when this is passed into another convolutional layer, now it would be, when it's convolving over these numerical representations of lines, it would be learning more like shapes, like, because again, it's applying this filter to detect a pattern over something that's already a pattern, like a line. So you can think of it in terms of these higher level abstractions that you're hoping the network is learning. And there are some visualizations that I'll jump into at the end where people look at the after training a neural network, they look at the gradients of the input to see how much each like pixel contributed to the classification. And then you can see that some of these networks learn to look at like sometimes funny things, like when they detect if something that some image is a cat, it does so by looking at like the tail and the nose or something. You know. But the hope is that these convolutional layers are that are learning these lower level abstractions that then they can stack to find again like lines, and then from lines or from pixels find lines, from lines find shapes, and so on and so forth.
So one question I have is that usually whenever you see the pictures of neural network with CNNs, you have this CNN layers in between, starting point and the end point, right? But doesn't it make sense to have convolutions in different ways, in different directions? So you start from the input and you put in your convolutional layers in one way, and then you start from input and you can put another convolutional layer, set of convolutional layers in another way.
So what do you mean by in one way and in another way?
So depending on the weights, you may be starting to focus on a different set of features, and depending on another set of weights, you may be starting to look at another set of characteristics. So it may make sense to have multiple networks, both starting from input and using a different set of convolution layers with different weights.
Yeah, so you can, okay, so this is related to two separate things. Let's see. So one thing is you could argue that adding more filters would really achieve the same type of thing. So because if you add another filter, you know, these are an independent column that learns for each, that still looks at every channel, just learns its own weight. So it learns its own representation of what it thinks are important, or what it thinks is valuable. So you could argue that this is functionally equivalent. Do you agree or disagree?
So I'm not quite sure.
I actually had a question about the filters.
Sure.
Is there like a standard filter that most CNNs use, like a Gaussian? Or do they let you choose which ones you want to use?
So the filter is learned by the network. So it's initialized to like, you know, some random values or some small random values likely. And then these filters are what this layer tries to optimize. Does that make sense? I can try to explain it better.
Yeah, that makes sense.
Okay, cool.
So imagine like you are in a room which is filled of junk, and somebody asks you to see and describe what you are seeing, and then you start focusing on the elements in the junk, and then you say, okay, what I see is that some of them are square boxes, some are rectangular, some are others. And that's way you can describe one way. The other would be, okay, I see, some green colored things, some red colored things. And then you can start a third way where you can say, okay, I see some utensils, I see some books, I see some containers. So there may be different way in which you can start to focus and drill down into describing the contents what you are seeing. So I was imagining that maybe convolutional layers will be used to begin from input in multiple ways.
Yeah, so I think that the filters should be able to achieve basically that. So we could imagine that if this layer only had one filter, it would only produce this top output, this top like 3x3. But adding that second filter, and then we could imagine that we have another convolutional layer being trained in parallel, which only has one filter, say filter W1, that's producing the second one.
Yeah.
But since the multiple filters in a single convolutional layer are learned independently, are like the outputs are computed only with respect to these filters in the or one specific filter in the input, that adding another layer in parallel should be like the equivalent of adding more filters to it.
More filters, right? Got it. Thanks.
No problem. All right, so is that a question?
Yes. So as Himanshu mentioned, like if you are looking at an image and you have two objects in it, for instance, then the convolution neural network might be able to say there is one object A and an object B. So that's a possibility, right? Like model can output two answers.
So are you talking about the whole model or the convolutional layers specifically?
I'm talking in general with respect to classification using CNN.
Okay, so some of this has to do with the model or the whole overall or overarching neural network architecture itself. So you could structure it. If we go back to this one again. So this is a softmax. This one produces a probability distribution that it belongs to one of these classes.
Okay.
You could also do a multi-class sort of classification. Where basically you produce where you're not assuming that the whole thing is a single probability distribution. You'd have to replace this so it's no longer softmax, but you'd have to squash each one of them into a probability distribution. So you probably use sigmoid instead. So if you replace softmax with sigmoid, remembering back that sigmoid, is used for binary classification. So that would be like doing a bunch of binary classifications at once, which would let you do basically like a multi-class classification.
Okay.
Then that's also different though from saying like, I see one car, one truck, two cars, two vans. And that's where we're, let's see.
Yes.
So okay. That one's also possible. I need to think of the right like architecture to do something like this. So you could do something where you're, this might be a decent segue into recurrent neural networks. The only downside is that recurrent neural networks are, usually the output is ordered. So I'd have to look, because image segmentation, or when people are training neural networks for image segmentation, which I actually haven't really done, they are doing essentially something like that, where they're selecting regions. Now I'm not sure if they're doing it a class. Let's see. I'm not sure if they're doing it as a classification on the pixel level, because that would explain how you would come up with segmentations for. Here, I'll just show an example. There's a tutorial on this as well. I didn't include it in this one, but I'm pretty sure.
Yeah, I think my question was like, you could do like different classifications, right? So
yeah, so you can do multi-class. This is
okay.
The convolutional layers themselves don't really restrict what you can do, what you're doing with the output. They really just determine how you want to process your input and whether or not you want your network to be biased towards these spatial regions. Now,
Okay.
when I say biased, the reason why I say it that way is because technically you could imagine each of these as inputs. So if you look at one of these filters, you could imagine that this filter is actually like, let's look at the red channel in filter 0. We could imagine that instead of using a 3x3, or like we could imagine that this is essentially, or we could reconstruct a fully connected layer that does this same thing. We would just have a lot of 0 edges. Because here we're doing the pointwise multiplication. So that would be like the input multiplied by the weights. And then we're summing them. And all of these extra regions that are outside of this 3x3 region on the input would just have 0 weights going into this output, this -6 in the output volume. Does that make sense?
Yes.
Yeah, so basically, given a convolutional layer, you could construct a fully connected layer that computes the same thing. But using a convolution kind of like, I guess, biases your network to only look at ones in a certain region when it's trying to learn something important, which kind of imposes this this spatial information or spatial knowledge, I guess, or bias towards collecting spatial knowledge. So hopefully that makes sense. I want to just drive home with that it's not more expressive. It's not like this does something that a fully connected layer couldn't, but it is something that it does do something that you wouldn't want a fully connected layer to do because it'd be a lot harder problem because it would be able to look at all these other things and it wouldn't force it to only look at this region for lines and things like that. It could pick up on all sorts of other noise to try to learn something. All right. I mean, we don't need to go through these a huge amount, but I should have pulled these up when I was talking about activation functions. You know, ReLU's in the top right, the one I've mentioned a few times, max between 0 and a value. Sigmoid is here on the left. I mean, here they have some rules with them about ReLU is faster because of course it's easier to compute than division and exponentiation. There are extensions to ReLU, and this is why it gets a little bit complicated, and there are a lot of papers about this stuff. And I can like link to that or show some things there. Or, I don't know. It's actually available in DeepForge's help message for each layer. but they have other fixes on top of ReLU, like leaky ReLU or parameterized ReLU. All sorts of other options there. And softmax, of course, forces something into a probability distribution. I'm going to skim over this a little bit. Now, max pooling or pooling layers behave similar to this. So like each color-coded region, top left being green, you know, and then the red, and then the orange and the blue. Each of these regions represents essentially the equivalent to like what our convolutional layer was looking at a given time. So we're using a 2x2 kernel, and we're taking a stride of size 2. So this first looks at the top left quadrant, and it selects the maximum or the largest number there, so 100. Then it looks at the next one and just selects the largest. So rather than doing a scalar product, we're just simply doing a max or a min or an average. Now, as they say in the third bullet point here on the left, it is more aggressive, of course, because you are losing the information around it. So there are some advantages to using convolutional layers, but the idea, or I guess some intuition behind something like max pooling, is that it gives you a little bit of robustness, I guess, about inputs that are a little bit shifted or adjusted. So like, for example, supposing 100 meant that there was a cat here, you would, this would allow, doing a max pooling here would essentially allow the cat in this kind of contrived example to be in any of this upper left quadrant, rather than requiring it to be in a specific cell. All right. I'm not gonna go through I mean, if people have questions about these, I'm happy to go through it, but given the time, I'm probably gonna jump to recurrent networks. Of course, if anyone has any questions, feel free to jump in and stop me. All right, let's see. Oh, dang it. Sorry, embarrassing. I had the slides open there. And let's see. I hadn't realized that it hadn't opened in a new tab. All right. So, all right, so let's get into recurrence or recurrent neural networks. Now, just like how convolutional neural networks are, or convolutional layers are used to process 2 or 3-dimensional input where you're looking at regions at a time to kind of detect these local patterns. Recurrent neural networks are designed to be able to handle variable length input or variable length output. So essentially here I talk about how regular neural networks are stateless. You put an input into the function, it produces an output. Whereas recurrent neural networks have some memory built in so that they can see what, so that they can essentially make their prediction or inform their next output based off of history as well, rather than just relying on the current state. Now, one of the challenges with, I mean, there are a few challenges with recurrent neural networks. One is
examples. Can you give me examples of variable length inputs and outputs?
Sure. So image captioning. So that's kind of blending convolutional layers with recurrent. So if you were captioning an image, you want to, given an image, produce some variable length output of text. So you might try to train a network that you feed an image into, and then it should produce not just a single piece of text or a fixed length of text, but it should produce words or characters, most likely. It'll produce characters until it. So usually you encode a stop character. So it would produce characters until it produces a stop character.
So
you could also think about.
That will be an example of a variable output, a variable length output.
Yep, variable length input could be like training an agent in a video game that's looking at multiple frames. You can either do frame stacking, where you just feed in 3 or 5 or something frames at a time, or you could use a recurrent neural network where you can feed in 1, 2, 3, all the way up to however arbitrary many you want to feed in. Another example is automatic machine translation. So you feed in text in one language, a character at a time, and then it outputs text in another language, a character at a time. Okay. Now, some of the challenges, like I mentioned here, are exploding and vanishing gradients, because when you do back propagation through a recurrent neural network, the current prediction, in other words, when you produce an output and then actually I have a better slides for this. So 1 second, I'll just jump to some slides and then use those so I don't have to just try to ask you to imagine. All right, so CNN architectures, let's not talk about those too much. There are a bunch of them. It is worth pointing this out. There are a lot of off-the-shelf, like convolutional neural network architectures and things like that you can try, that are at least a good starting spots. You don't have to try to make them all from scratch. Anyway, so there are a couple, like I mentioned, you can handle variable length input. Oh, look, they use image captioning as an example as well. But you can do variable length output, variable length input with one output, many to many, like sequence to sequence, things like that. All right. Yeah, so this is not largely important. It's kind of interesting, but there was a paper where they did an image classification problem using a recurrent neural network, feeding a pixel in at a time, which was pretty interesting. All right, so I don't care about this part. There we go. All right, so so basically when you're computing some value, you have some initial state that so like initial memory, I guess, or state for the recurrent neural network. And then you feed some input in, so X1 in this case. And that produces a new state, as well as a new output. Here we go, so we have these outputs here as well. So, and then we feed the new H1, so the new hidden state, and the input X2 into the network. And then that produces both an output, Y2, and a new hidden state. So you can continue with this kind of arbitrarily long. And each of these can also will have their own loss computed from each, because if we're doing a prediction at each time step, there's of course a loss that could be computed from it. Now the tricky part here though is that means that there's a lot of, this makes our graph much longer. And if there is like a large gradient, like you can imagine how this could make exploding gradients, which already can be a challenge, or which can already happen, can be even more of a problem now when we're making our computational graph much longer, because we're computing, because we're invoking our neural network multiple times. Does that make sense?
Yes, I think so.
Yeah, and this is why it's kind of tricky to cover so much in a little bit. Like that's why I try to stay bird's eye-ish, but hopefully concrete enough. All right, so now we're going to get into some of these like demos and hands-on examples. Let's see. Okay. So the example that I used before is another one that we could certainly use. Oh, here we go. Here's the one I was just looking for. So I'm not going to go through this in a lot of detail, since this is technically the same example that we used last week, but I am going to call out the part that Himanshu asked about last week, which was the architecture itself. So basically we are given some images or some input, or some of these, oh, actually maybe not everyone was here. Basically we have some small images. Is there a question?
Could you, yeah, Brian, this is Yogesh. Could you please maximize, like not maximize, increase the font size? Is there a way?
Is this helping?
Yes.
Cool. All right, so.
Thank you.
Yeah, no problem. All right, so we have images that look like these, so small images, and then we're trying to train them. Now, this is an example in PyTorch, but here you can see it's a pretty small convolutional neural network. So like we're using a two-dimensional convolutional layer. I believe this first value is the kernel size. Oh man, I'll have to double check the docs. All right. Okay, here we go. Input channels, output channels, and then kernel size. All right, so so this is taking a 5x5 sliding window, and it's expecting three input channels, so red, green, blue. It's using 6 filters, and using a 5x5 sliding window. And then it's taking I believe this is just gonna be a 2x2 sliding window over each of the inputs. And then it does another convolutional layer where it's expecting the 6 filters, or sorry, it's expecting the 6 channels from before. It's producing 16 channels, so it could be looking for also like a pretty like large variety of shapes and patterns and stuff, and but still using a 5x5 kernel size or like window size. And then it's flattening the inputs. So then it's flattening our inputs and connecting it for this fully connected layer, which is producing 120 output neurons, which has 120 output neurons, then 120 down to 84, then 84 down to 10, where each of the 10 is corresponds to each class. One quick second. Oops, sorry about that. All right. Okay, so I just wanted to kind of jump back to this example just to show, or just to be able to give a little bit more context to the neural network architecture itself, since now that we've looked at some of these convolutional layers and pooling layers and things like that. I'm not going to go through this whole thing since we did last time, but if people, unless people like object and want to. There is an example here as well doing image segmentation. I like this classifying names example. This is just going through a character at a time and trying to predict whether or not the name, what nationality the name comes from. So in other words, this is a many to one sort of network. You could argue that they're actually almost all many to many. It just depends on really how you use the output. So for example, in this case, if you're doing a character level RNN, where you're passing in a character at a time into this recurrent neural network, just like the figure that we showed earlier, and it's producing like Y1, Y2, Y3 for every time step. One way to view this is that it's producing a different prediction for each character, and you could train it accordingly. But like in this context, like another way of viewing it is more like refining a single prediction. Does that make sense? So
yes, I think so. So it's kind of similar to what you experience when you are doing a Google search. As you start typing in the characters, you already see the available choices getting changed.
Yeah. Yep. Yeah, exactly. So like when you would, if you type something like that, that could be implemented as like a recurrent neural network where you're, every time they type a character, you're not there are two, you could do that statelessly, or you could do it as an RNN. If you did it statelessly, every time you type a new character, I would take all of the text you've typed and I'd feed it through a network. Now, if I did it statelessly like that, since it's a variable length input, I would have to, if I wanted to avoid a recurrent neural network, which I would not recommend doing in this use case, but if I wanted to, you could have padding. So you could say, I support lengths up to 10 characters long. As they type, they type the first character, you have one value for the first character and a bunch of zeros. You feed that through and you get a prediction. They type 2 characters. Now you have 2 characters set and a bunch of zeros and you feed it through. Computationally inefficient and not really ideal, and not really the best way to model it. Whereas if you we're setting it up more like this example that we showed from these slides, you would it would be more like whenever the user types a new character, like suppose they type x1 and 2, and then when they type x3, you don't recompute anything from x1 and 2, but you output y3, which would be your most up-to-date prediction. So essentially, you could treat it like an anytime algorithm. And that's one thing that's kind of fun about this one. And it's nice because you're doing it all from scratch, including like representing your individual characters, all this kind of fun stuff. So I think it's a nice exercise, though we don't have time to do it right now. It's a nice exercise for working with the recurrent neural network, or working with recurrent neural networks. Now, one other little thing, just to do a little bit of, I guess, self-promotion. I don't talk about the neural network architecture in here a huge amount, but this was one of the research projects I was working on at Microsoft Research. And I was using a recurrent network in this setting. Basically, darn it, I was hoping I should have probably posted a picture of the architecture because I have one somewhere. Maybe I'll have to update this. But basically in this setting, we had a bunch of states being fed into an AI that was trying to predict what it thought a human would go after or interact, what element in the environment that a human would interact with next, whether or not that's like picking up a weapon or attacking an enemy. So it was trying to predict things like that. And it had a similar architecture like this, except every output was what it was going towards at that point in time. So I put the first state in, and then it produces what it thinks it should do at that state. We feed the next state in, it produces a different, or maybe the same goal. And then we continued on that way. Now, the big thing worth mentioning is just like when I talk about the neural network architectures and how the neural network architecture can be kind of tailored to your task, be it regression or classification or multi-class classification or anything like that. And it depends on really how you train it and usually the end of the network or the architecture. Similarly, RNNs are largely like the interpretation of an RNN's output also depends a bit on how you train it. You know, so like I could train this where so you could train it where, given like text or characters from an input name, I keep computing the loss with the ground truth at the end the whole way through. So I could say, like, if I know that this name is going to be Scottish and I feed you a G, I'm going to penalize you if you don't say Scottish, which is a little strict at the beginning anyway, but by the end you should have hopefully captured enough. Hopefully you should have been provided enough information to where it actually could have been learned. Similarly, like you can also just train at the end and then try to backprop through. There are different approaches, and or you can be sometimes you might actually have labels, like in the case with the game. I might have labels for every time step. So you produce an output, like Y, I'm going to call this Y hat 1, or a prediction for time step 1. And I compare it to the ground truth at time step 1. You produce a different prediction at time step 2. I compare it to the different prediction at time step 2, and so on and so forth. So there are different ways that these can be trained, and and it depends a bit on the specifics of the problem. But the big takeaway is, if you're working with two-dimensional data where it's spatial, or where there should be looking at like regions of information for patterns, looking at something like a convolutional neural network is going to be really helpful there, because that's already biased to look at regions at a time to try to detect patterns, as opposed to fully connected layers where they're connected to anything and everything. Now, recurrent neural networks are really relevant when you start getting into either sequential input or sequential output. RNNs are a decent place to start, recurrent neural networks, but there have been other ones as well, because RNNs can be known for being kind of forgetful, in the sense that their decision is biased towards the most recent data that they've seen. So they can forget things from like a while back. There have been some layers to try to address this, like LSTM, or long short-term memory. LSTMs basically store long-term information separately from short-term information, so that they don't have recent information or recent information really overwriting older information. There are other mechanisms like attention mechanisms, where they try to prioritize inputs. So you basically pay attention to different parts of the input, and you try to learn what to pay attention to. And there are other approaches like that, but it's hard to try to cover all of those in a short section like this. So I'm hoping that in talking about big picture, why do I care about convolutional networks? Like, when am I going to use them? Talking a little bit more concretely about what a convolution layer does, and then trying to do something similar with recurrent, hopefully gives you enough of a lay of the landscape, so that if you have more questions, you know where to look at least, and dig into some of those. That said, I do have some other links at the bottom of this that I would recommend checking out. GradCam is just another way to visualize or understand what was learned by the network. You can also do saliency maps that basically say what did the network think were important features in this image when it produced this output. And I think I already talked about training networks with CMAES last week. Basically, there are other ways to train networks. If they're small, you can be more creative with evolutionary approaches like this one. If they're larger, you're probably going to want to stick to backprop. The nice thing about some of these evolutionary approaches is they can be trained in parallel. So if you have other bottlenecks and the neural network weights are relatively small, there could be motivation to look to alternative methods. And then the one last thing I'll just try to sneak in here, I guess, is this thing that I didn't have as much time for this week or last week. But basically, when I was looking at this visualization, you can actually think of it as like a computational graph. So basically looking at what were the inputs to each operation, and how this, what were the inputs to each operation, producing some output, which then is fed into another operation, and basically keeping a history, like a tape of all of the operations that have been performed. And if you do something, and generally right now, in like, especially in like TensorFlow and PyTorch, these approaches, basically they use operator overloading on some of your regular mathematical operations, so that they can record the history, and this is how they perform automatic differentiation. Now, the details of that aren't hugely important, except that they do it differently, where like PyTorch is computed on the fly. In TensorFlow, I have to look at eager mode a little more, but at least in TensorFlow version 1, they used a static graph where you would have to basically build the structure of computation. So say like this thing multiplied by this thing, and construct this whole graph, and then run it, and then create a session to run it in. Whereas PyTorch, you basically just wrote standard Python code, and since it was relying heavily on a lot of this operator overloading, it just built the graph on the fly and behaved accordingly. Anyway, I just wanted to throw that little tidbit in there. Sometimes people, like there are a lot of people who are big fans of PyTorch, and I confess I'm one of them as well, because when you're using it, especially for research and stuff, it's very flexible, and you can just do the computation rather than think about the graph and constructing a graph to do the computation where you're one step kind of removed. Anyway, so I think with that, I'm open for questions. Again, I felt like I was trying to cram in maybe more than I had time for, but but hopefully it was informative and helpful.
Thank you.
Yeah, no problem.
I don't know how much time we have, but last week you were showing the DeepForge, and when you showed I think it was LSTM or some other neural network, but there were a couple of elements in there. One was the dropout, and the other was the autoencoder. I don't know. Can you tell a little bit about those?
Sure. So I talked about the autoencoder. The autoencoder itself wasn't in DeepForge. I guess I don't really need to pull it up for this. So dropout basically just zeroes out some proportion of the inputs. The idea is to try to basically make your network a little more robust by making sure it doesn't rely on just a couple star players, so to speak, if you're thinking of the neurons themselves. Does that make sense?
So isn't it similar to the weights and the filters in the convolutional layer?
So the dropout actually doesn't require two-dimensional layers or sorry, it doesn't require like two-dimensional inputs or things like that. All it does is actually I will pull this up. All it does is zero out just zero out some fraction of the inputs.
Okay.
It's supposed to help with overfitting and generalization. So let's see. I think we have an example of it here in this network. All right, so we open this guy. This guy's quite large. All right, so I thought, here we go. Here's my little help message. All right, applies dropout to the input. Consists in randomly setting a fraction rate of inputs to zero at each update during training time, which helps prevent overfitting. There is a paper here as well. So I can post this in the chat if you're interested. The paper that introduced dropout.
Yeah,
basically,
sure.
What's that?
Sure.
Sounds good. Basically, the idea is that suppose we had like 10 neurons and you found out that in your training data, you know, like once it ran through all of this, the 8th neuron was like a dead giveaway for what the answer was. If we use dropout and we zero those neurons out periodically, then you're requiring the network to rely on other inputs as well, and not just relying on a single, like a smaller subset of good neurons or things like that.
Okay. Okay. Yeah, I think it makes sense.
Yeah. So it's. All right, now, as far as autoencoders are basically. All right, so basically what you do is you take some larger input or some larger representation. You have a network that's structured kind of like a bow tie. In other words, it has a bottleneck in the center. Now this bottleneck in the center, so you can do it with fully connected layers. It doesn't have to be convolutional or pooling or anything like that. But it has this bottleneck in the center, and then it tries to blow back up to produce some sort of output. Now you train it by trying to make sure that the output reconstructs the input. So in other words, you often do like mean squared error or something like that with the output on the input or given the input. So the idea is that hopefully you can find a more compact way to represent your inputs, which hopefully corresponds to like meaningful features in your data. Does that make sense?
So maybe a little. So with the convolutional layers, you are focusing in on specific features and optimizing the network that way. And with the autoencoder, you are further blowing it up, which is kind of like a step backwards. But maybe it's a better representation than you begin with in the input layer.
Yeah, because convolutional layers are downsampling, as we could see in the volumetric view.
Yeah.
Like your inputs should be getting smaller as you go because you're looking at regions and producing smaller outputs. Whereas, yeah, an autoencoder is actually a full neural network architecture rather than a single layer. And it starts by, again, it's a neural network architecture with this shape where it tries to have a really succinct or small representation in the middle that hopefully it can blow up and reconstruct the input from. Yeah. An example would be like, oh, let's see. Okay, here's an example. Do you guys watch Ellen's Game of Games ever?
No.
Okay, well, there's one game, and there's probably a more regular household game for this, where someone is told some word or something that they need their partner. What's that?
Are you showing something? Because I'm not seeing it.
Oh, no, I'm not. I'm just.
Just go ahead.
I probably should show something, but no. Basically, suppose we're playing a game, and they have one like this on Ellen's Game of Games. That's why I tried to reference it. But suppose we're playing a game where I have some word and I want to convey a message to somebody else, and I can only do it with like one word, or I know I have some phrase and I want to get the message through with one word. Basically, you're trying to get I would try to pick a word that hopefully succinctly captures important qualities that'll remind the other person of it. But I wouldn't pick words like the or of course. I'd try to pick something like Garfield, you know, like it's kind of a pretty weak analogy, but it's a similar thing that you're trying to train the network to do. It's provided a bunch of inputs, which are a bunch of numerical inputs, and it wants to condense it into something that, given this, it could blow it back up, and not any information about the original input. Given this, you want to have some, you want to be able to reconstruct the input itself, and you're hoping that if you can construct some meaningful representation in the center, that you can get a really close approximation of the input in the blowing up phase. Because it's worth mentioning that the compression and decompression, or encoding and decoding phase, are of course stateless, so they don't know about the original input, so it's not like they can cheat. They just, given a small set of features, can we blow it back up to what the input?
Okay. So let's say we start with an input, we give it to an autoencoder, and out comes a compact representation of the input. But if we give it that compact representation and run it backwards, it may also convert back to the original input that we came up with, maybe not exactly, but very close.
So can you see my figure
Yeah.
now?
Yeah.
So that's basically what we're looking at, except
Okay.
Except they are two separate units. So there's an encoding phase and a decoding phase.
Mm-hmm.
Try to compact or put it into something really small that the decoder can decode.
Right.
And then if you're able to reconstruct the output from the input, the assumption is that this code or this representation in the center is something that's meaningful in the data. Like
Okay.
you learned like how to say, it's a picture of a cat, and the decoder knows how to make a cat. You know?
Right.
Mary, it looked like you had a question.
Yeah, so is there going to be more discussion about saliency maps, and then also about latent space analysis stuff?
That's a good
I keep
Yogesh
hearing
question.
that I don't know much about.
Yeah, no worries. So that's a good question for Yogesh. What do you think, Yogesh?
He's not here.
So I mean, sorry. I'm happy to talk about latent representations and saliency maps. Now, saliency maps are actually relatively. So the funny thing about a saliency map is it's essentially, so you know in calculus when you first learn how to take the derivative of the output like dy over dx. The funny thing is that a saliency map is basically computing that. It's just how does the input contribute to the output, and then we just want some way to visualize it. usually with the saliency map, they're doing it with images, but you could certainly look at the saliency of any input to a neural network. And the big key thing here is that these neural networks are composed of these differentiable functions. Since it's all differentiable, we can always just differentiate with respect to the input. And if we, and that'll differentiate the loss, the error with respect to the input. And that'll give us an idea of how did each pixel value contribute. And if we have that, that can do, that'll basically tell us the relative importance of pixels, or at least what the neural network thought at that point. I don't know if that example is super helpful now, but I'm happy to talk more about it if people are interested or want to hear more. Probably not right now since we're almost 20 minutes over, but.
Okay, thank you.
Yeah, no problem. What do you? I mean, if you can also email me too if we don't go into it more in the AI seminar, and I can always just provide more feedback or set up a call or something.
Okay.
Basically, I'm happy to be helpful. Whether or not
I'm
we can.
definitely trying to understand terminology still.
Yeah, no worries. One other little thing that one last promoting. So I did. I don't know if I showed this before, but there is an example here that's showing some of these same concepts, but in NetsBlocks, like with a computational graph, tried to be like that's shown here and stuff. So if people are curious and want to check out this version too, I don't know, I was playing with it a little bit, or playing with some of these things and making them by hand. Because a lot of the concepts are similar, even though of course that example's not working with like large data, nor is it very efficient because it's in a block-based language in a browser. But, all right.
All right. Thank you.
Yeah, no problem. Hopefully this was helpful and informative or something. Great. Well, if there aren't any other questions, I think this will probably conclude the meeting for the seminar.
All right.
And let's see. Yeah, and I guess I hope to see you guys next week. I'll have to ask Yogesh what the plan is and things like that. But if there are any other questions, feel free to reach out to me and stuff, and I'm happy to be helpful as much as I can.
Yeah, thanks for your time.
Thanks.
Yeah, no problem.
Bye.
See you later.